So we'll talk some about Chapter 11, and we're going to tie this to both X-ray interactions. And so we're no longer talking about particle interactions. We're talking about interactions between X-ray photons and atoms within the patient's body or the area of interest. So, the type of X-ray interactions that occur with matter are coherent scatter, which is sometimes called classical or Thompson or even Raleigh scatter, all describe the same kind of coherent scatter. These happen at very, very low energies. In fact, Raleigh scatter is what's responsible for the redness of sunsets, is Raleigh scattering within the atmosphere. So it's interesting from a scientific or physics point of view. It does not play a role in diagnostic imaging. The ones that are of most interest to us are the Compton effect and the photoelectric effect. These are the ones that we're going to spend most of our time focusing on, because these combined effects result in what we would call attenuation, which just is another way of saying that they stop the X-ray beam. One of them is a little bit more efficient at stopping than the other, and they both happen in different percentages within the body based on differing criteria. Pair production only happens at energies over, I think it's 0.0, or it's 1.06 something MeV, mega electron volt. So pair production is only important to the therapeutic range of energies, right? It is not a diagnostic interaction, but it is a photon interaction. It's an X-ray interaction with matter, is that it can basically split a neutron in half, resulting in the creation of a electron and a positron, which then typically mutually annihilate each other. It's a very high energy interaction. Photodisintegration is again another very high energy, generally at energies over 10 MeV and higher. We could have a photodisintegration event in which the photon actually destroys a portion of the nucleus of the atom. So the ones that are of most importance to us are Compton and photoelectric effect, but there's a number of different interactions that can occur largely based on the energy of the X-ray photon. So the first that we will look at here is what we will call coherent scatter. I don't think our textbook touches on coherent scatter at all. Double checking. No, it doesn't. But this again might also be called Raleigh or classical scatter.
Coherent scatter? It's on 188.
Oh, 188. Okay, thank you. .188 coherent scattering. In general, these are very, very low energy, but it does not result in ionization of the atom. It results in excitation of the atom, and that can be excitation of either the atom itself or excitation of a single electron within the atom. And so I don't think we necessarily need to get into the specifics of what, whether it's Raleigh or Thompson scattering that's occurring, as long as we understand that they are all forms of coherent scatter. They're called coherent because the energy of the incident X-ray is the same as the scattered X-ray. All that's changed is the direction. All that has changed is the direction. The atom, again, has not been ionized, and the photon retains its energy. It changes its direction. Okay? Again, this happens at very low energy ranges. Compton scatter is hugely important. This is significant for us as X-ray techs because it can result in noise on the image receptor, as well as dose to us who are working in this field. The number one source of our X-ray exposure as X-ray techs is going to be not the tube, but the patient. I'll say that again. The number one source of our X-ray exposure is not going to be stuff leaving the tube. It's stuff coming off the patient. And the reason it is coming off the patient is because of Compton interactions. Okay? The degree or angle of deflection for the photon is going to directly determine the amount of energy that the photon has. Right? So its resulting energy is related both in the binding energy of the electron it interacts with, so it will ionize the atom, and then it's going to go off on a different direction. And the angle of deflection and the ionization process are what are going to determine that photon energy. And if you see the initial energy, as indicated here, the initial photon energy here is greater than is greater than the energy of the second photon. So one of the ways it's written that here is the wavelength is the wavelength there is less than the wavelength of the second photon. So in other words, the frequency is higher with the initial photon than the second one. Okay? The significant takeaway here is the energy is there's energy lost because the original photon has a higher energy than the photon that's produced through Compton scatter. So energy is lost in the ionization of the atom, and then the photon continues on with reduced energy. You tracking with me on that? Okay. And this, again, can happen within any cell, within any atom, within the patient's body. Okay? Compton effect is not dependent on the Z number of the atom or of the number of electrons or anything like that. Photoelectric effect differs from Compton in some major ways. The first way is that it generally occurs with K-shell electrons. So the energy of the photon is going to be close to or equal to the energy of that K-shell electron. It will, so again, I said Compton could happen with pretty much any electron, any atom, anywhere in the body. Photoelectric effect is going to be very specific to that K-shell binding energy. It will ionize the atom, so it will eject the electron, and that electron is now called a photoelectron. Okay? It's now called a photoelectron. The X-ray photon has been completely attenuated at this point. So the energy that it has given off was solely captured by that photoelectron. It is dependent on the electron binding energy, and so it relates directly to the atomic Z number of the tissue. I'll say that one more time. It is related to the binding energy of that electron, and so it directly is tied to the Z number, the atomic number of tissue. Why is that important? Basically what I'm saying is we would not have diagnostic x-rays. The whole science would not exist if we did not have the photoelectric effect. Compton effect, all it does is it increases noise and scatter and potentially occupational dose. Photoelectric effect is the reason why we can take pictures of things. Right?
Can you say that one more time with the related to binding energy?
Yes. So the photoelectric effect is related to the K-shell binding energy of the electron. So it is also related to the atomic number of the atom. So as the atomic number increases, the potential for photoelectric effect also increases. It is more likely that atoms with high Z number are going to stop X-ray photons with the photoelectric effect. So one way to think about that as an X-ray tech is that bones show up white on the X-ray, and something like with air in it, like the lung, shows up black on the X-ray. Why is that? Well, some of it has to do with the density of the part itself, but a big part of it has to do with the fact that bones have a higher Z number, therefore more photoelectric effect occurred, more X-rays were stopped by the bones, so less X-rays made it to the image receptor, versus within the lung tissue, there's a lower Z number, and so less photoelectric interactions are occurring, more X-rays are making it to the image receptor to expose it. One way to think about this, and I can't stress this enough, that we would not have a diagnostic range of X-ray energies if we did not have the photoelectric effect. One thing that's always been helpful to me is to think about Compton as being bad, right? So I think about the NWA song Straight Out of Compton, right? And think about, okay, it's a good song, but it's talking about bad, rough things happening. Why? Because of the pressures of the streets in the Compton area, north of San Francisco, right? Check out the song sometime, Miss Marshall, you'll love it. So I think about Compton effect being related to Straight Out of Compton. It's not a way, it's not a situation I want to find myself in. Whereas photoelectric effect is actually what won Albert Einstein the Nobel Prize in physics. It was not the theory of relativity. It was his work with photoelectric effect. Why? Because it is how night vision goggles work. Right? So we can harness photons of a bunch of different energy levels in this way. And so that photoelectron we can capture as well and use it to power things like night vision goggles. We can use it to increase the amount of light that we're perceiving. We use it as X-ray technologists as a way to differentiate between soft tissue and bone. So we've directly tied it to different attenuation values. So when I talked earlier about subject contrast and how that's related to different, what we call absorption differentials or attenuation differentials, that is directly tied to photoelectric effect, because photoelectric effect is directly affected by that atomic number of tissue. Okay? But the basic interaction, again, is that an incident X-ray photon gives off all of its energy to ionize an atom. So it results, again, like with any ionization process, in an ion pair of a now positively charged atom and negatively charged photoelectron. Pair production, again, is only going to happen, I think it's at 1.06 MeV and higher, maybe it's 1.02 MeV and higher. So this is outside of the diagnostic range of energies. We could have a photon interact with a neutron, completely destroying the neutron and producing an electron and a positron. Now, a positron is a really weird thing. It has the same mass as an electron, but it has a positive charge, right? So it's not as though some new particle was produced. The theory is that that is essentially what makes up part of a neutron. is an electron and a positron somehow sandwiched together, and so it results in a neutral charge. But a positron is strange. In fact, I'm trying to remember which physicist it was. One of the physicists who worked at Oak Ridge posited that a positron is an electron moving backwards in time. They have very short periods of life, like measured in nanoseconds, because what they do is they very quickly interact with another electron and they mutually annihilate each other. When they do that, they produce very, very specific energy, almost like a characteristic kind of energy of 0.51 MeV photons traveling in 180 degree directions opposite each other. Why is that important? Why do we care? This is exactly how PET scanning works. It is positron emission tomography. So if we put a receptor over here and a receptor over here, and we've injected someone with a radioisotope that is known to cause pair production, we can track where those pair production events are happening inside the body. Because statistically, we can say if there's a hit on a detector over here and a detector over here at the same time, I can pinpoint with great precision where that positron emission initially occurred. Right? So why is this important? Pair production is important because of nuke med. Photodisintegration, again, incident X-ray of 10 MeV or higher results in the ejection of a nuclear fragment. This only happens in therapeutic ranges of energies. So, we've talked a little bit about differential absorption. This is not an illustration that's found in your textbook. It comes from the Bouchon book. One way to, so this is one way to think about it kind of graphically. Another way to look at it here in your textbooks on page 191. I actually kind of like the illustration on 191 a little bit better, but this is yet another way for us to think about it, so it's helpful to think about things as many different ways as possible. So in this illustration here, we have an X-ray tube, and it is producing all sorts of X-ray photons, right? And it's incident on this patient here. And within the patient, we may have scatter events. We may have some of the X-rays being transmitted through the patient to reach the image receptor, and then we may have some photoelectric absorption. Both the scatter events and the photoelectric absorption, if they result in the photons not reaching the image receptor, then we're going to say that they are resulting in a differential absorption. I like the illustration on page 191, like I said, a little bit better because it shows roughly 1,000 X-rays incident on a volume of tissue, and you can see as the tissue density increases, the numbers of X-rays are falling off with each density difference of the tissue. So that's a large part of how we produce X-ray images. So let's think about how those interactions occur. What are the predisposing factors that are going to allow us to see differential absorption if this is how we make pictures? Okay? If the atoms within a given volume have a higher atomic Z number, photoelectric absorption will increase because it is more likely to occur with the higher Z number. PE just in this case means photoelectric absorption. Okay? Compton scatter, on the other hand, is unaffected by Z number. So this is a big plus for photoelectric effect and a big minus for Compton effect. Right? Just another kind of bullet point in our case against Compton effect. As we increase the KVP, here's the problem. Photoelectric absorption decreases sharply. statistically it will decrease in its percentage of occurrence, right? But Compton scatter remains proportionally the same. So if you can imagine what I'm saying graphically, let's draw it out here. So this is a percentage of interaction over here on my graph, and this is energy of in kVp, let's say. Let me erase this. kVp. We could also put it in keV, or kilo electron volts, but we'll talk about it in kVp terms. So as the energy increases, I'll indicate photoelectric in red. Photoelectric falls off, right? Compton remains proportionally about the same. It moves up maybe just a little bit. But you can see somewhere in this general area right here, the percentage of Compton interactions just eclipsed the percentage of photoelectric interactions. Do you see what I'm talking about? So Compton didn't change that much, but because photoelectric effect started to fall off as I increased the kVp, I now have proportionally more Compton interactions occurring within the patient. Okay? So I cannot just endlessly, even though I've said that kVp, as I increase the kVp, I potentially am reducing patient dose. I'm also decreasing the amount of photoelectric effect that is occurring. Right? That's a big deal. So we're going to spend a lot of time unpacking that. It's a major part of why we have classes called image evaluation. But for us right now, we just need to go ahead and memorize this. That as photoelectric, as kVp is increased, photoelectric absorption decreases sharply, while Compton scatter remains proportionally the same. If we increase the mass density, like what is illustrated on page 191, we will see an increase in both photoelectric and Compton effect. So both photoelectric and Compton effect are tied to the density of the tissue that we are trying to image. Okay? So Compton actually kind of gets a plus here, right? But it got a negative here, and so it's come away with just this one plus. It does, in some ways, contribute to differential absorption. Okay, here's another way of thinking about it. I want to present us with as many ways to think about this as possible. So if I have a high atomic Z number, photoelectric absorption will increase. Compton doesn't care. So the overall transmitted X-rays will decrease. How do I think about that? Well, one way to think about that is like bone, right? Bone has materials in it that have a higher Z number plus increased density. So it attenuates more of the X-ray beam due to photoelectric absorption. So less X-rays get through bone. So bone is going to show up white on my picture. Less X-rays were able to get through it. Higher kVp. As I increase my kVp, this slide is incorrect, I think. Bear with me here. As I increase my kVp, this is not right. Photoelectric absorption will reduce. Compton effect will relatively increase. Like what I just illustrated on that slide, it will proportionally increase. There's a range of energies from about 200 kVp to roughly 1 MeV, in which all that is going on is Compton effect. It's just noise. It's like that radio station where it's just noise. There's nothing else going on. It's just noise. And then all of a sudden we get into weird, kind of higher energy stuff that happens. But there's a reason why our X-ray tubes, we can dial in a mass of 500, but the highest kVp we can do is like 120. Because anything higher than 120, we are no longer harnessing the photoelectric effect. You tracking with me?
Can you talk about this, like how it affects a patient or something else?
Yeah.
'Cause
Yeah.
charts just confusing me.
The charts aren't helping. Okay. So let's think about it this way. Let's start with a high kVp, right? And I want to make an X-ray of a patient using a high kVp. What's going to happen within the patient? Say I turn the kVp up to, in this imaginary situation, 200 kVp, right? And I'm going to make a chest X-ray at 200 kVp. The X-rays that are hitting the patient are either going to just become Compton scatter or just go straight through the patient. So if I was holding up an X-ray plate to that, it would be like the radio station or like the TV when you get the static on the TV screen. All I would be getting would be noise and white space. Because all that's getting through the patient is things are just passing straight through the patient, and some things are making some noise. So no useful information is being transmitted at that high kVp, right? If I crank the kVp down a little bit, though, to like 100 kVp, so let's drop it in half and do a chest X-ray now. I hold up my image receptor. Is there still some noise? Yeah, there is still some noise there. So I still have some Compton interactions going on, but I also have got the kVp low enough that I am getting photoelectric absorption going on. So the X-rays, if they hit a bone, they're going to stop. If they hit oxygen within the lung, they're going to stop. And those stoppings of the X-ray are what's resulting in a picture. Right? The stopping of the X-ray is what's making a picture. It's not the X-rays passing through. Another weird way you could think about it is to look at text on a page, right? And do this little funny experiment, right? Like imagine we could make this page to where, like I don't know if you've been on a website or something where the page itself is black and the text is white. So imagine you're thinking about, you're looking at a page and the page itself is black and the text is white, right? Would you be able to see the text if it was black? No. So that's what's happening with this high kVp. It is just blackening. So I can no longer see the letters. I can't read anything. But if something stops it and turns it white, then all of a sudden I can see the letters. Okay? So the other way to think about that is what makes it through and what doesn't. Right? So, because that is what differential absorption is referring to. It's saying there needs to be something that changes the way stuff is absorbed, otherwise I can't see anything. If everything's just absorbed the same way, like if X-rays just uniformly get through all, or they are uniformly stopped, right, then there won't be any difference or values to see, right? So all of these factors play a part in what gets through and what doesn't. So as I increase the Z number, I would expect to see less X-rays getting through. So that's going to show up white on my picture. As I increase my kVp, I would expect to see more X-rays getting through. So the X-ray is going to look darker, right? The mass density of the patient themselves. So if I'm X-raying a chest versus X-raying a hand, if I increase the mass density of the area being X-rayed, less stuff is going to get through, right? If we think just about the chest, though, here, it gets kind of interesting because we have what we would call high subject contrast. I have an area that has lungs, so there's air and stuff, and I have an area that has bones and muscle. And so what allows me to see the difference between the bones and the muscle and the air is just this issue right here of whether my kVp can sort those two things out. whether I'm having enough photoelectric effect to stop some things and not stop others. I don't know, did that help a little bit? Okay, good. Thank you for the question, to know what is going on with our thinking. So here is that example of a chest x-ray. And what I've said is x-ray quality equals beam penetrability. So how many of the x-rays can get through the part? And we're talking about producing trillions of these things. Every time we turn on the x-ray machine, we're producing trillions of x-rays. Right? So trillions of these photons are coming at the patient. They're hitting their skin. Some of them are getting through the skin and some of them aren't. Right? Now they're hitting the bones of the ribs. Some of them are getting through the bones and some of them aren't. In fact, the ones that are getting stopped most likely by the bones are getting stopped by photoelectric interactions. So there's a differential thing going on now. Right? Some of them are getting it through and some of them aren't. The ones that get through the lungs, right, they're able to pass through there pretty easily because there's not a lot of dense tissue there. But now they've got to hit the ribs on the other side. Right? So enough of them are stopped in this travel through the patient's body to give us whiteness where the ribs are, grayness where things like muscle and skin are, and then the darkness on the image where there's mostly air. I like looking at pictures of chest x-rays because I feel like if we can make kind of the one shoe drop on a chest x-ray, the other shoe is quick to drop as well in terms of our understanding of this. Okay? So I'm going to talk to you briefly about subject contrast within the chest. Okay? Subject contrast within the chest has a high subject contrast. Why would I say it has a high subject contrast? I think we've touched on this. What's inside the thorax or inside the chest?
Air.
Air? Good. What else?
Muscle.
Muscle and bone. So between the air, we have a low density, right, with a high density structure being the bone. Right? So it is a high subject contrast, meaning there's a big difference between the air and the bone. Now, from the x-ray point of view, this is where things get kind of weird, right? We want to capture as much contrast as possible from this structure, right? So we need to think about those differential absorptions that occur between the air and the bone, right? And we need to set a technique that is going to allow us to kind of decrease the high contrast that's occurring. Because we don't necessarily want a high contrast, we don't necessarily want a low contrast on all our pictures, we want an optimal contrast, something that's going to show as much diagnostic information as possible. So our job as x-ray techs is to think about what we know about these x-ray interactions in the body and change our technique according to the area of the body we're trying to image. Okay? That's the name of the game. We're going to be imagining what is inside the area I'm trying to picture and how do I need to change my technique in order to capture that information. So, I think he touches on this. If he doesn't, we need to go ahead and think about it some now. Because what we're talking about when we talk about kilovolt peak or energy of x-rays, quality of x-rays, how many of the x-rays are likely to penetrate through the anatomy and how many are going to be stopped. The best way that we have to measure that is what we call a half value layer. And it's the thickness of any given material to reduce beam intensity by a quantity of half. Right? say that again. It's the thickness of any material to reduce beam intensity or the quantity of X-rays passing through the material by half, right? So when we talk about quality, a lot of times what we're talking about is half value layer. Every single tissue in the human body has different half value layers, right? And this is just yet another way to think about this. That means that if I have a volume of lung tissue, or a volume of bone, or a volume of noses, or a volume of eyes, every single organ is going to have a different half value layer. So if I were to measure the number of X-rays that were able to get through those various tissues, I could know that is roughly the half value layer. That is the attenuation value of eyeballs. That is the attenuation value of bones. That is the attenuation value of soft tissue like muscle, right? And so as I'm able to measure those different attenuation values, I can see differences on the image itself, right? That is exactly what the image receptor is doing. It's starting out with trillions of X-ray photons that are hitting the patient. Some of them are getting through and some of them are not. The ones that get through hopefully are stopped by the image receptor, right? And the number of the ones that got through is directly related to the half value layers of all the different tissues that those X-rays had to go through. Okay? Why this is especially important, one of the reasons I'm stressing it now, is this is exactly how CT works. This is how computed tomography works. But it is also how digital X-ray works. So whenever we're looking at a digital X-ray picture, the way that we look at it is a representation, right, of anatomy and different colors and values. That's not what the computer sees. The computer sees statistical values of different half value layers. It sees different intensities that got through at different levels, right? So we can do some statistical work and figure out what the half value layer, and it can depend on the X-ray energy as well as the absorption material. And all of this, the reason I'm stressing this now, and the reason I'm telling you about this now, is this is the reason why we're able to see things on an X-ray picture. Is every single tissue in the body attenuates things differently. They have different half value layers. Okay. So let's talk a little bit about ways that we can improve the detection of different half value layers. Well, it would actually be helpful to us if we had a narrower beam of X-rays. And by that I mean if we continued to have a spectrum of energies, but that spectrum was more clearly defined, right? So this graph is showing the number of X-rays on one side and the X-ray energy on the other. So over here at this X-ray energy, we have this number, right? We've said that the ideal beam is the one that has a very narrow spectrum. So it is this rainbow here, right? If we do not filter our X-ray beams, though, because of the way that Bremsstrahlung works, we would have the predominance of our energy X-rays would be very, very low energy. There would be a lot of X-rays that are very, very low energy, right? And so this would be roughly how our spectrum would look, with the addition of this little spike here for characteristic interactions. Okay? So again, not very helpful, because all of this stuff here, it's too low to even participate in photoelectric effect. It's more like coherent scatter type stuff, like Raleigh and Thompson scattering, Okay, now we're starting to see a little photoelectric, And the rest of this is just Compton interactions. It's just Compton scatter. Right? So that's why we're saying we would like to see a beam just right in here. Why? Because this is where the predominance of interactions are going to be photoelectric. So what are we going to do? We're going to add filtration. We're actually going to stop some of the X-rays from ever exiting the X-ray tube. We're going to use filtration. So when we filter the X-ray beam, you can see we've knocked off, we've reduced all the way down to here. We've stopped all of those X-rays that were weak, that were useless. And we start to see a spike close to what's related to this curve here. We start to see an increase in numbers as we get closer to photoelectric energies, right? And then a fall off of numbers related as we start to get to the energies that cause Compton interactions. So this is yet another way that we are going to try to increase attenuation and better view subject contrast. Now I want to just point out real quick, and we'll spend a whole chapter talking about filtration. But I'm not talking about you adding anything to the X-ray beam. So I think here, this is a filter that might be added to the X-ray tube manually. So it would be a compensating filter, right? I would actually add this myself to the X-ray tube, and I would call it a compensating filter. But what I'm talking about is the total filtration of the X-ray tube system itself. So within the X-ray tube, there's a beryllium or aluminum window, and that is going to be responsible for about 0.5 millimeter aluminum equivalent. There's some filtration that is natural to the X-ray tube. Then there's what we call added filtration that is in the form of a filter placed right here between the tube and the collimator, as well as the mirror itself that reflects the collimator light. Those we would call added filtration. The total filtration for all X-ray tubes that operate at energies of 70 keV and above, or 70 kVp and above, is 2.5 millimeter aluminum equivalent. That's required by the government. Okay? So the government's recognized that we need at least this much filtration to safely operate the X-ray tube. Why? Because not everything that's being produced in here is helpful. We need to filter out the bad stuff. The stuff that is not responsible for what? Differential absorption. The stuff that does not help us see differences in the anatomy of interest. So, one more time, we'll go through this one more time. The factors affecting quality and quantity, and I said that quality we've related to beam penetrability. It's how much of the X-rays can pass through, what power they have. Quantity, we've said, is the number of X-ray photons. So again, quality we typically relate to kVp, and quantity we typically tie to mass. That's not perfect, but it's close, right? With quantity, anytime we see an increase in quantity, that could be related to an increase in kVp. An increase in mass is directly proportional to an increase in mass. It will decrease, quantity or intensity will decrease with distance, and it decreases with filtration. Okay? On the quality side, we see quality or penetrability. Those terms can be used interchangeably. Half-value layer can be increased with increased kVp and increased filtration.